Good evening, everyone, and welcome. While everybody's finding the last few seats, I'll do a little bit of housekeeping announcements. I'm Matthew Greenberg. I'm interim head of the Math and Stats department here in the Faculty of Science, and it's great to have you with us this evening, whether you're joining in person or online. Today's Louise and Richard K. Guy lecture marks the 19th year we've been offering this series in honor of Louise and Richard. It's an amazing privilege to be able to continue Professor Guy's wish of sharing the joy and beauty of mathematics with everyone. Again, couple of housekeeping notes. For those of us joining us in person, the closest exit is through the doors behind us on either side of the stage. Also, we're recording tonight's event. We'll be posting it to the Pacific Institute of Mathematical Sciences MathTube channel. After tonight's talk, I'll be moderating a question answer with Professor Cameron. For those in the room, we'll have a roaming mic, and for those joining online, we'll have a number on screen that you can use to text our team, and they'll ask your questions for you. Now, I'd like to introduce Dr. Kristen Bates, Dean of Science, to come and say a few words.
All right, well, thanks, everyone. Before I start, I always love doing this. I have a lot of people in the back without a seat. Raise your hand if you have an empty seat beside you. Okay, guys, find a seat. Come and join us. So thank you, everybody, for coming today. I'm Kristen Bates, the Dean of Science at this wonderful faculty here at University of Calgary. And before we begin, we are only 4 days away from our National Day of Truth and Reconciliation, so it's extra important that we recognize the wonderful lands that the city of Calgary is on. We are located on the traditional territories of the Treaty 7 region in southern Alberta, which includes the Blackfoot Confederacy, comprising the Siksika, Piikani, and Kainai First Nation, as well as the Tsuut'ina First Nation, and the Stoney Nakoda, which includes the Chiniki, Bearspaw, and Good Stoney Nations. And the city of Calgary is also home to the Métis Nation of Alberta, Districts 5 and 6. In Louise and Richard Guy lecture series is really a phenomenal tale and represents so much about what the Faculty of Science represents. So this was an amazing gift that Louise gave to Richard on his 90th birthday, an endowment that allows us to have these amazing talks and reach out to the community so that we can all love and embrace and understand the magic that is math. And I think this is probably the best birthday present I have ever heard of, because let's face it, most of us have everything we need in life, and yet to give the gift of science is truly special. And this lecture series really does empower people to think about the beauty of math and to inspire all those next generations of researchers and to bring in the community. And I know a lot of you have heard the faculty has launched its new strategic plan, Get Science Done, and at the heart of that is community. We want to engage with as many members of the community, young and old, and from around the world as possible. And this is a perfect example of that lecture series. In the 19 years we've had this series, over 4,000 people have attended this lecture. And I think from today's turnout and online, we could be hitting 4,500. That is a phenomenal gift that Louise and Richard Guy have given not just to University of Calgary and the city, but they've given it to around the world. And I encourage you, if you have not already done this, we offer a series of lectures, public lectures, from Earth X, biology, all across, and we would love you to join. And so there will be a QR code that you can learn and register for all our wonderful events that we do here. And these events are about inspiring people to enjoy science. And science in all its forms, including Sudoku, which you could think of that as a gateway to the love of mathematics. Because how many people here have done a puzzle? How many people here have done it for 30 minutes at a time? Oh yeah, hours at a time, for sure. And it's because it is, once you get into it, it is fascinating. It engages your mind to think of different pattern recognitions. Think about math in a fun and engaging way. So it is really a gateway game to the joy of mathematics. So I am super excited about this lecture today, and though I've been told I will not come away with better tips and tricks to beat my dad, I still hold up hope. So with that, I'd love to invite back Matt to introduce Dr. Cameron to the stage. Thank you.
It's my privilege to introduce tonight's distinguished speaker, Professor Peter Cameron, who joins us from the University of St. Andrews in Scotland. Just the most recent stop in an illustrious mathematical career that has featured lengthy tenures at both Oxford University and Queen Mary University of London. Along the way, Peter has supervised 45 PhD students. He wrote 14 books and authored almost 400 papers in 19 mathematical disciplines, according to the categorization of the American Mathematical Society. And all of this in collaboration with well over 200 co-authors. Peter has been decorated with prestigious awards. He received the Senior Whitehead Prize of the London Mathematical Society in 2017, nearly 40 years after earning the early career incarnation of the same award. In 2013, he was honored with the Euler Medal for distinguished career contributions to the field of combinatorics. In 2018, he was elected a Fellow of the Royal Society of Edinburgh. In my 16 years at the University of Calgary, I've had the pleasure of attending many Louise and Richard Guy lectures, spending time with many of the speakers. Of these, I really think that Peter reminds me the most of Richard. He certainly shares Richard's infectious joy in doing mathematics of nearly any sort with almost anyone. And like Richard, Peter clearly prioritizes and enjoys the mentoring of young mathematicians. Among his 200 co-authors are many junior trainees, likely drawn into the subject in part by Peter's openness and enthusiasm. As many of the mathematicians in the audience likely know, Peter has kept a blog for 15 years, still going strong, sharing his mathematical thoughts and insights with the entire internet community. Had Richard been born a generation or two later, I can certainly see him having done likewise. He would certainly have liked the tagline of Peter's blog, always busy counting, doubting every figured guess. Ladies and gentlemen, please join me in welcoming Professor Peter Cameron.
Thank you very much, Matt. Can everybody hear me all right? Good, thank you. Yes, I woke up with a bit of a cough this morning, and I'm a bit croaky, but I'll try and keep going. So, thank you. So, it's a great honor and pleasure for me to be giving this lecture. But I won't tell you anything much about Richard and Louise, because many of you knew them better than I did. But I will just say one thing. I was at a conference last year, a big international conference. It had a section on game theory. And I learned at that section that people who work on game theory, the game is played by two players called L and R. And these maybe once stood for left and right, but now they clearly stand for Louise and Richard. And I think that's a very fitting tribute to them, actually. Thank you. So, Almost all of you know what Sudoku is. There's an early example, 2009, from one of the daily papers. And of course, the rules, which you probably know, are you have to put the numbers from 1 to 9 in the empty cells. Each number should occur once in each row, once in each column, and once in each of the 3 by 3 squares outlined by the dark lines. The British newspaper, The Independent, gives this statement after telling you what the rules for Sudoku are. There's no mathematics involved. Use logic and reasoning to solve the puzzle. Well, have you ever seen a better definition of mathematics than logic and reasoning? This is obviously mathematics. And the only thing that they could possibly have been thinking is that there are some variants of Sudoku, like Kakuro and Killer Sudoku, where you actually have to add the numbers up. And they think that adding the numbers up is mathematics, but using logic and reasoning is not. Well, I hope I'll have convinced you by the end of the evening that there is mathematics in Sudoku. There are close connections. And so I want to go to the history a little bit. Here's a list of names. One of the people on this list invented Sudoku. But I remember reading a supplement in the daily paper once about Switzerland. 10 things you didn't know about Switzerland. Number 7, Euler invented Sudoku. Not true, but he did have an important role to play in the story, as I'm going to tell you. So I'm going to say a little bit about where Sudoku comes from and how it ties in with other things that mathematicians have been interested in for 2,000 years. This isn't a lecture on history, so I'll be a little bit cavalier with some of the facts, but I'll get the story across, hopefully. Here's Euler, and he posed this problem in 1782, the famous Euler's 36 officers question. You have 36 officers. They come from 6 different regiments, and they hold 6 different ranks. And each combination of a rank and a regiment is represented by one of the officers, right? And you want to know whether you can arrange them in a 6 by 6 square on the parade ground so that each, if you go down along any line of the square or down any file, you see each rank once and each regiment once, right? Can you arrange them like that? Well, he wasn't the first person to consider that sort of question. Ozanam asked whether you can do a similar thing with the 16 court cards in a pack of cards, Jack, Queen, King, and Ace. So 4 values, 4 suits. Can you arrange them in a 4 by 4 square with each value in each suit, once in each row, once in each column? And now, just to point out to those of you who aren't mathematicians, to a mathematician, those problems are identical apart from the fact that one has 4 in it and the other has 6. The fact that one is about Prussian army officers and the other is about court cards in a pack of cards is irrelevant. Mathematics is the art of stripping away those irrelevancies to get to the problem that you can actually think about. Well, Ozanam was able to solve his problem, and there's a solution. You can check that the conditions are satisfied. If you just go along the first row, for example, you see Jack, Queen, King, and Ace, and you see diamonds, hearts, spades, and clubs. Right? So there's a solution. You can check all the others if you want, but that works. Euler thought that his problem had no solution. There's the experimental method. They couldn't get them in quite the right place. There was always 2 that had to fight for a particular place. Anyway, Euler thought that the answer was no. But why was he interested in that problem? Well, this goes back to something called magic squares. Magic squares have been an obsession of, I would say, an obsession of humanity for 2,000 years. Certainly something that mathematicians in many cultures have thought about. And the Chinese were first, but many other cultures have thought about these things. And part of the reason for that is that some cultures regarded a magic square as a kind of talisman, that if you wore it on your armor in a battle, you would survive the battle intact. And so obviously an important thing to have. So I would say mathematicians 1,000 years ago working on magic squares are a bit like the people working on Bitcoin at the moment. But anyway, sorry. Here's Duret. His famous engraving Melancholia from 1514. So a rather sad-looking angel with various mathematical things, spheres and polyhedra and so on. Up here, you can't really see it properly, but there is a magic square. And I've enlarged it here for you. The numbers 1 to 16 arranged in a square. If you go along any row and add up the numbers, down any column, or down either of the two diagonals, they'll always come to the same answer, 34. And you can check a couple of cases of that if you like. But there's something else about that. I told you Euler did this picture in 1514. He arranged that 1514 were together in the bottom row of the magic square. So there's enough flexibility in building these things that you can do tricks like that. All right. Why was Euler thinking about the 36 officers? Well, he'd come up with a new construction of magic squares. There were many constructions that had been given by the Chinese, the Arabs, many other cultures, but Euler had found what was apparently a new construction. And so here's how a mathematician will describe it. And if you're a mathematician, you can read what is written there, but I will explain it to you, assuming that we have a 10 by 10 array. So we've got officers from 10 different ranks and 10 different regiments, and we want to put them in a square so that each rank and regiment occurs once. Well, we number the officers not from 1 to 10, but from 0 to 9, and there's a reason for that. And we number the ranks are numbered from 0 to 9, the regiments are numbered from 0 to 9, and in each, suppose we have them arranged like this on the parade ground, we make a 10 by 10 array, and in each cell we put the rank and the regiment of the officer in that cell. These are numbers from 0 to 9, remember. So if you look at all the numbers written in the cells, you'll have 0, 0, 0, 1, all the way up to 9, 9. So if you just think of them as numbers, they go from 0 to 99. Now, why is this anything like a magic square? Well, if you think about one row of that square, every rank occurs once in that row. So the units digits in the numbers you see in that row will be 0, 1, 2, up to 9. They add up to 45, right? And the regiments, similar thing. So the tens digits will also go from 0 to 9. So they will add up to 45 times 10, 450. So if you add all the numbers in that row, you'll get 495. And the same will be true for any column. So he's constructed a square in which each row and each column add up to 495. The only trouble is that that starts with 0, and some people are a bit prejudiced against 0. They want their square to start with 1. So Euler says, just add 1 to all the numbers in the square. Instead of going from 0 to 99, they go from 1 to 100. And what have we done to the sums? Each number in a row, there are 10 numbers in that row, each has been bumped up by 1, so we've added 10 to the sum, so it's now 505. So we get a square in which all the row sums and all the column sums are 505. You still have to fiddle with it a little bit, probably, to get the diagonals to work out right. But there are only 2 diagonals. There are 20 rows and columns, so we've done the bulk of the work. So that was Euler's idea. If you can find this arrangement of the offices, then you can build a magic square. Now, Euler called a solution to this problem a Greco-Latin square. So now I've got to explain to you, why did he call it a Greco-Latin square? Well, I'll show you. So I've taken the numbers of the ranks and regiments to be 0 up to n minus 1. Euler is going to say, we'll use Latin letters for one and Greek letters for the other. So here's a small example, 3 by 3. So there are 3 ranks, A, B, and C, and there are 3 regiments, alpha, beta, and gamma. And you can look at that and check. Every combination of a Latin letter and a Greek letter occurs exactly once in that square. So that's good. That's the kind of thing we're after. And each Latin letter occurs once in each row or column, same for each Greek letter. So Euler's method says, now turn them into numbers. And if A, B, and C are 0, 1, 2, and if alpha, beta, gamma are 0, 1, 2, you will get this. So C beta, for example, becomes 2, 1, like that. A gamma will become 0, 2, and B alpha becomes 1, 0. But now this is not 21, 2, and 10, because there are only 3 symbols. So we'll take these to be in base 3. So if you think about doing this sum in base 3, 21 will be 2 3s plus 1. That'll be 7. So what you'll actually get will be this square, 7, 0, 2 is 2, 1, 0 is 3, and so on. And then the last step is you add 1 to everything, and you get 8, 3, 4, 1, 5, 9, 6, 7, 2. So this is essentially the Chinese Luo Shu square, which is the only 3 by 3 magic square up to fiddling around with it. So anyway, that's Euler's construction. But now he has the problem of how do you arrange these offices on the parade ground? How do you produce a Greco-Latin square? Well, and also, what is a Latin square? Latin squares are very popular these days. Lots of people study Latin squares. But why are they called Latin squares? Well, if you go back to the Greco-Latin square, if you just forget the Greek letters, that's a Latin square. So it has n symbols, and each row and each column contain each symbol exactly once, right? You might see that we're getting a little bit closer to Sudoku here, right? Anyway, so Latin squares have a lot of applications. I'll just take you, I think I'm still all right for time. I'm running a little slow, but let's see. I'll take you quickly through some of the applications in cryptography and statistics. So the only provably secure cipher is the one-time pad. How does the one-time pad work? You want to send a message, a string of symbols in a fixed alphabet. So you need a key, and the key is a random string of the same length in the same alphabet. And then you need a Latin square, which uses that alphabet as its symbols. Then, to encrypt data symbol X with key symbol Y, you look in row X and column Y of the encryption table. You see what is written there. It's Z. That's what goes into the ciphertext. So, for example, if that's your plain text, rather boring message, but you might want to send it, and that's the random key, then there's the Latin square. What do you get? Well, in the first place, you've got plain text letter A, key letter C, so you go to row A in column C and you see an A. So the first symbol will be an A. And you work through the whole thing like that, and you get the ciphertext. So as I say, that's an unbreakable cipher. Of course, it might be breakable. The enemy might have broken into your room and stolen the key. And it has other drawbacks. The key is as big as the message. So in order to use this, for example, if you're sending a spy out into enemy territory, that spy has to have a copy of the key before they go. And that key has to be as long as all the messages that they're going to send back. And that may be a problem. Rumor has it that back in the day, there was a secret room in the Pentagon where people just sat there tossing coins to produce random sequences so they could send their spies off with these random sequences. Well, I don't know whether that's true or not, but it has to be random. Yes, if the encryption table is not a Latin square, then it's not unbreakable. Either it won't work properly. If you have an entry repeated in a column, if you see that entry, you don't know which of the two input letters produced it. If you have an entry repeated in a row, you can still decipher, but you've leaked some information to the code breaker. So here, just for interest, sorry, we're not going back. Oh, okay. So this was the substitution table for one of the Japanese ciphers in the Second World War. Spot the flaw. Who can spot what's wrong with that? Yeah. Row 8 has repeated numbers. Yes, it has 2 pairs of repeated numbers. There are lots of flaws. There are 2 zeros there. So I'm not saying that's why they lost the war, but maybe they should have been a little more careful. Right. So orthogonal Latin squares. This is just Greco-Latin squares under another name. You've got 2 Latin squares, and you say that they're orthogonal if, when you take one and the other, you plonk the second one on top of the first. Each pair of symbols occurs precisely once. So if you go back to our Greco-Latin square there, you see there's a Latin square there, CAB, ABC, BCA, and there's another Latin square, even though it's got Greek letters in it, beta, gamma, alpha, alpha, beta, gamma, gamma, alpha, beta, and each combination occurs once. So that's a pair of Latin squares which happen to be orthogonal to each other. So that's what you need for Euler's idea of constructing magic squares. Euler knew that he could make this construction work as long as the number n was not congruent to 2 mod 4. In other words, n did not leave the remainder 2 when you divided it by 4. If you try to work out 2 orthogonal Latin squares of order 2, you'll easily find that it can't be done. 6 is the next case. That's the case that Euler was unable to solve. And 10 would be the next case after that. So that was completely unknown back then. Euler was right about 6. Tarry proved this in 1900, essentially by enumerating all possibilities. But subsequently, somebody found a letter that the German astronomer Heinrich Schumacher had written to the mathematician Gauss, saying that his assistant, Thomas Clausen, had just solved Euler's problem and shown that you couldn't do it for n equals 6. But Clausen's papers have never come to light, so we've no idea whether that's true or not. Do you have a question?
So does this mean that the magic square from 1 to 36 is not possible, by the way?
You can have a Latin square. Yes, you can. A magic square. You can. No, there are many constructions for magic squares. You can build a magic square using. Yes, you can build a magic square of that size, but Euler's method will not work. That's all I'm saying. Euler invented a new method for constructing them, but he couldn't get it to work for 6. But apart from that, he was as wrong as he could be. In 1960, Bose, Shrikanda, and Parker found a construction that gave orthogonal Latin squares of every possible order, except for 2 and 6. So all the numbers that Euler couldn't do, apart from 6, they managed to do. And so they're called the Euler spoilers, which is a good way of reminding students how you pronounce Euler's name. Right, in statistics, come on. Latin squares are used to balance treatments so that if you're testing agricultural things, for example, pesticides on beans, there might be some systematic variation. That there's a row of trees there, and maybe the insects crawl out of the trees and tend to attack things on the right-hand side. So in order to balance that, you can use a Latin square. Now, if you look at this, it is an actual experiment, and one of the treatments was no pesticide, and I think you can probably spot some of the squares that had that treatment, the ones that the bugs have eaten all the bean plants. Anyway, so suppose you're doing an experiment in an orchard where the trees are laid out in a square, and you put the treatments on using a Latin square. But you come back the next year and you want to do a different experiment. Well, if you use the same Latin square, then each thing that got treatment A last year will get treatment alpha this year, and maybe you don't want that because those treatments might interfere with each other. So instead you should use orthogonal Latin squares for that. And that means that the first year you should make sure to use a Latin square that has an orthogonal mate, and not all of them do. Right, so this principle was pushed a little further by Berens in 1956. So he said, suppose we have an n by n grid and it's divided up into n regions. We want to put the treatments on in such a way that each treatment occurs once in each region. So for example, you might have a field with 5 by 5 plots, and there might be a boggy patch in the middle which might affect how the plants grow. So you'd like every possible variety of plant to be exposed to that once. And so here's a way of doing it. So this is what Berens called a gerechte design. That basically means a fair design. So it's fair because everybody suffers equally if there's a boggy patch in the middle, right? Okay. Now, orthogonal mates are gerechte designs. So I'll just briefly show you that. There's a Latin square, right? I've done it in numbers and also in colors. And I use the entries in that Latin square to define my regions. So there they are. So the things that had a 1 in them over here will now be in red regions, and 2 in green and 3 in blue. Now I've got to put the numbers 1 to 3 in so that each number occurs once in each different color of region. Well, there it is. You can check. So in the red region, for example, there's a 1, there's a 2, there's a 3. So that satisfies Berens' definition of a gerechte design, even though back in the one before you could see the regions were sort of connected bits. Here they're not. But never mind, it's still, according to the definition, it's still a gerechte design. Okay, so now we come to John Nelder, who invented something called a critical set in a Latin square. So he wanted to fill in some of the entries, but be sure that there's only one way to complete it to a Latin square. So let's suppose you were given this. Well, you would know that, for example, in that square, it can't be 1, it can't be 2, so it must be 3, and similarly that square, so you can immediately do that. Now you have 2 rows and 2 columns, each having 2 entries, so you can fill in the third entries, and there's only 1 square left, and it's obvious what must go in there, and there's your Latin square. So those 2 numbers, oops, sorry. Those 2 numbers in there form a critical set in that Latin square. Now, you can see that we're very close to Sudoku now. I'll skip this bit. I don't think we need this. The point is, we've got this notion of a gerechte design. We've got this notion of a critical set. Put them together, you've got Sudoku. But the statisticians missed that. and it was up to Howard Garns, one of those names on my list. Howard Garns was a retired architect in New York. He invented this puzzle and published it in a puzzle magazine. Well, it had quite a history after that. But you see, if you have friends who aren't at this lecture and you say, I learned what Sudoku is. It's a critical set for a Gorector design in the 9x9 grid partitioned into 3x3 squares, right? But at least the point is, I said mathematicians abstract. We've now got these notions of critical set and Gorector design. We can recycle them into many other applications as well. But so here's the basic thing. So Garns called his puzzle number place. It went to Japan, and they called it Sudoku. And then Wayne Gould publicized it back in the West, and it really caught on in a big way. Wayne Gould, incidentally, was from New Zealand, but his brother was a British politician back in the 90s, I think. So that's Sudoku. Now, that's Sudoku, but to a mathematician, Sudoku isn't terribly satisfactory because we've got words to describe things, but we haven't got a method of turning it into things that we understand better and attacking it. So I'll just take you through what Robert Connolly did. Robert Connolly works on rigidity of structures, things like geodesic domes. Why do they stand up? And stuff like that. But he invented this thing that he called symmetric Sudoku. So this square here just looks like an ordinary Latin square at first, but it is, if you look a little harder, it's a Sudoku solution. But it's more. Every row contains all the numbers once. So that's the first condition that we want for a Latin square, and similarly every column. Now, to be Sudoku, we have to have these 3x3 subsquares containing the numbers each once. But he went on and defined 3 more regions. And they're called broken rows. So you take, for example, the example I've shown here is you take the first big column made up of 3 of the squares, and you take the little rows in the corresponding positions in those 3. So the bottom row in that square, the bottom row in that square, and the bottom row in that square, they should have all the numbers 1 to 9 each once. And similarly, broken columns, same kind of thing. Each number should occur just once. And finally, locations. So I've chosen here the bottom left entry in each of the 9 subsquares. Each of the numbers occurs exactly once in all of those. Right, here it is in stained glass. David Spiegelhalter, who's the Professor of Public Understanding of Risk at the University of Cambridge, his hobby is stained glass. And when he learned about this, he decided to construct it in stained glass. Right? It's actually rather nice, and you can see various patterns in it if you look. But is it art? Now, I understand that you had a lecture about mathematics and art last year, so you should be well primed for this question. So think back to that Duret engraving with the melancholy angel. So probably if you were to update that, the angel would be writing on a tablet and would have a computer on the desk. He might have something like that on the wall in place of the magic square. And then you would probably say, yes, it's art. But if I go back to this, oops, is that art? Mathematically, it's absolutely identical to David Spiegelhalter's thing with the colors in it, right? But I think there are not many people who would regard that as art, and most of those would probably be mathematicians. But there's, as I say, there's David Spiegelhalter. I'm sure that it's art. It's a beautiful object. Anyway, I'll just flash this up. You can make symmetric Sudoku puzzles if you wish. So here's one. This has a unique way to complete it to a symmetric Sudoku. I'm not going to leave that up there for you to copy down. If you want to take a picture of it, do so. But the slides will be here, and if anybody wants to get hold of a copy, you can. Sorry, I've gone too fast. It has a beautiful mathematical structure, much nicer than regular Sudoku. And I want to say a little bit about that. There are only two essentially different solutions to symmetric Sudoku, precisely two. And when I say essentially different, of course, if you shuffle around the first 3 rows, the second 3 rows, the third 3 rows, and same for the columns, or if you make a substitution on the numbers, that's more or less the same thing, right? So apart from doing that, there are only 2 possible solutions to symmetric Sudoku. And the proof of that takes things from all over mathematics and beyond. Affine geometry, perfect error correcting codes, and the card game Set. How many people here have come across Set? Quite a few. That's good. That's good. So, I mean, apart from this piece of work, we had 2 encounters with Set. The first was when Gary Gordon and Liz McMahon came to spend a sabbatical in London. Their daughter was the US Set champion. And so, of course, they introduced us to the game. Then we were in New Zealand, and Hans Hockey was very keen on Set. And what I'm going to tell you in a moment is that there's a natural way of matching up the cards in a pack of Set cards with the squares on the Sudoku grid. So I'm going to say a word or two about that. There are 81 cards. Each card has 4 attributes, taking 3 possible values. The values are number of symbols, shape, color, and shading. And to be a winning combination of 3 cards, either for each attribute they must all be the same, or for each attribute they must all be different, right? So there are 2 examples from the Set website. And you see in the first one, they're always purple, but there are 3 different shapes. There are these lozenges, these worms, and a diamond. There are different numbers, 3, 2, and 1, and there are different shadings. These are empty, these are hatched, and these are solid. Over here, the numbers are different, the shapes are different, the colors are different, but they're all solidly shaded. So those 2 are both winning combinations in Set. Now, Set, if I could describe it in a rather derogatory way, I hope nobody minds, it's like a kind of much more sophisticated version of Snap. So the cards are dealt out, and if you spot a set, you have to shout Set, and the first person to shout it gets the cards, roughly speaking. So you have to sort of train yourself to recognize these things and recognize quickly whether they form a set or not. Now, as I said, there's a correspondence between the cells on the Sudoku grid and the set cards. How does that work? Well, if you look at the Sudoku grid, it's 9 by 9, but it's divided up into these subsquares. So first of all, you look at which block of 3 rows it's in. Then you look at which row within those 3. Then you look at which block of 3 columns it's in. And then you look at which one of those 3 it is. So you've got 4 values, each 0, 1, or 2, if you count like that. And that uniquely identifies a cell of the Sudoku grid. But it's the same thing with a set card. It's got 4 attributes, each taking 3 values. So you can match up the set cards with the Sudoku grid. And Hans Hockey and I had a lot of fun taking a pack of set cards and laying them out corresponding to the Sudoku grid. But it comes into the proof that there are only 2 solutions to symmetric Sudoku. I'm afraid I can't show you what that is, but it turns out that you've got 4 attributes, each taking 3 values. That's like being in a 4-dimensional space over an alphabet of 3 symbols. So, if you like, over a number system with 3 elements, or a field, as mathematicians say. And the winning combinations in set are precisely the lines of the affine geometry. So we've got a geometry here with points and lines. The lines are the winning combinations in set. And that comes into the proof that there are only two symmetric Sudoku solutions. I wish I had time to tell you how that proof goes, because I think it's nice the way it brings in so many different things: error-correcting codes, finite geometry, and set. They're all there in the proof about Sudoku. What could be nicer? But Jarvis and Russell worked out the number of essentially different solutions to ordinary Sudoku. It's this rather large number, 5 billion. That being the case, it seems unlikely that newspapers are going to run out of Sudoku puzzles anytime soon. But this was quite a big computation, because what they had to do first, so what they were using, there's something in mathematics called the orbit counting lemma, which means if you have a structure with some symmetries, it counts things up to the symmetries. So when I say I'm allowed to shuffle around the rows within blocks and things like that, mathematicians will know, I'm telling you about a group, and that group is acting on the set of positions, and the orbit counting lemma counts orbits, as it says, and they're the essentially different configurations. So, but to start off with, I have to know just the answer to this supposedly simple question. Take the 9 by 9 Sudoku grid, forget about symmetries. How many ways can you fill the numbers in? How many different ways can you put the numbers 1 to 9 in, satisfying the rules? So this was an earlier computation by Felgenhauer and Jarvis, and they came up with this much larger number, but the symmetries cut it down from that larger number down to 5 billion, which is the answer for Sudoku. So that's the number of essentially different Sudoku filled-in grids, and that's the way, if you don't count symmetries, just count the number of ways of filling it in, it's that number there. All right, well, there are some things I haven't told you yet. How many Sudoku puzzles are there? This is completely unknown. By that I mean, how many critical sets are there in this corrector design? Or to put it another way, how many things could be printed out and would be a legitimate Sudoku puzzle, so would only have one solution? Well, nobody knows, but it's at least as large as the number that Felgenhauer and Jarvis got here, because each puzzle has a unique solution, and so there must be at least that many puzzles. So again, I say there's pretty good evidence that the newspapers aren't going to run short of Sudoku puzzles. What is the largest number of entries in a Sudoku? How many entries do you have to put in order for it to be possible to solve it? So there should be a smallest number for that, so that if you have fewer than that number, there won't be a unique solution. But if you have that number, it might be, if you've chosen well, that there is a unique solution. It's not Sudoku unless it has a unique solution. And there's a story about that too. One of the British tabloids, when Sudoku became popular, decided they were going to build the world's biggest Sudoku. So they found a chalk hill, and a chalk hill, it's covered in grass, but if you cut away the grass, the white chalk shows through underneath. So they cut this Sudoku puzzle into a chalk hill, and it was pointed out that it wasn't a Sudoku puzzle, it had hundreds of solutions. Sorry, is there a question at the back there?
By the way, I'm pretty sure I remember that mathematicians do not know what the largest number is. Was that in
I'm going to tell you what the answer is in a moment. 17. Better give her a clap. These three, Gary Maguire, Bastien Tugeman, and Gilles Savario, did the calculations, found that it's 17. It was suspected to be 17 for a long time. Gordon Royal worked very hard on this problem and found many, many 17-entry Sudokus, but was unable to find a 16-entry Sudoku. And he was fairly convinced that 17 would be right, but these were the guys who first proved it. So that's the smallest number of entries in a Sudoku puzzle. And if you want one, here's one of Gordon Royal's examples. So again, that will be in the slides if you want to have a go at it. You tend to find, as Sudoku solvers will know, that fewer entries mean it's probably going to be harder to solve, because more entries tend to force more things early on in the solving. But anyway, so Gordon Royal has quite a big collection of 17-entry Sudoku puzzles. So if you want a challenge, go to his website and take a few of those and have a go at them. That should keep you occupied for an hour or even more, perhaps. Anyway, that's Gordon Royal's puzzle. And that's the end of my talk. So thank you. But I'm sure you have plenty of questions, so please. Right.
Owen's going to run the microphone.
Oh, okay, right, yes. So have you got any yet? Does anyone want to ask a question now? Yes, there's one there. Is the mic coming?
Otherwise, you can just shout. The mic's important for the people who are listening remotely. So just a sec.
Thank you. Is it possible to find 3 or more Latin squares that are all pairwise orthogonal to each other?
Yes, indeed. In fact, it's known now that if you want, let's say, k Latin squares, any two orthogonal, as long as n is greater than some function of k, you can always do it. If n is a prime power, you can always get as many as n minus 1 orthogonal Latin squares. But for non-prime powers like 6, there don't even exist 2. But if you just want a fixed number, then as long as n is big enough, you can always do it. So these are quite hard proofs, but that is known now, yes.
Thank you.
Question over here in the front.
Got no questions in from online yet, so do send them into that number as we're waiting here. Where's the question? Right
here. What attempts, if any, have there been to compute the critical set size? Has there been, what sort of problems have people encountered in trying to solve that?
Well, I think I put it on my slide and I forgot to mention it as I went past. Nelder invented critical sets in Latin squares, and he conjectured that the lower bound was n squared divided by 4 rounded down to the integer below. That's not true. Counterexamples have been found to that. As far as I'm aware, nobody knows what the exact answer is in general. That's an open problem. But for small values, it is known. I can't tell you off the top of my head what the results are. But yes, it is something that people have looked at.
Other questions? In the back.
Back next.
Hi, very nice, so thank you. Has anybody looked into Latin cubes or hypercubes or things like that?
Oh, yes. Oh, yes. That's a bit of a minefield because, first of all, you've got to figure out what the right definition is. Do you want so if it's n by n by n,
yeah.
Do you want to have n symbols and each occurring once in each row, once in each line, once in each vertical thing? Or do you want n squared symbols so that each occurs once in each plane? And those are two quite different things. And people have used the term Latin cube for both of those and also for some slight variants on them. So it is a bit of a minefield, but there has been some thought about those. Indeed, one of the theorems that I'm proudest of with Rosemary Cheryl Prager, whom some of you will know, and Chaba Schneider, was precisely about, well, the three-dimensional case of it was precisely about a certain definition of Latin cubes, which just happened to do what we wanted. So Latin squares, I should have said this. There are zillions of Latin squares. Nobody knows a formula for the number of Latin squares, but it's n to the power constant times n squared. Now, when you stop and think about that, n to the power n squared is the total number of ways that you can fill in the square without any restrictions. So, you know, Latin squares are almost as bad as it can get. But with our definition, once you go up to Latin cubes, suddenly a miracle happens. If you have one of these things, out pops a group. And there are not that many groups. And the group uniquely determines the Latin cube. So for a suitable definition of Latin cube, there's one for each possible group. And then that goes to higher dimensions as well. That works in all dimensions. So this is a theorem that I'm very proud of. There's a question up here somewhere?
Yes, just got one from online as well to mix in here. So the question from online is, there are strategies to solve Sudoku puzzles. Are there any mathematically optimal strategies?
Oh. If there were, what would be the point of doing Sudoku puzzles anymore? Indeed, I'll tell you, my first reaction when I first saw Sudoku is, oh, a computer could do that. So I wrote a computer program. It wasn't a general computer program. It would only solve not too difficult Sudokus, but it would do it in a tiny fraction of a second. And so I lost interest at that point. And it was only when I was on a long train journey and somebody had left a newspaper on the train, I picked it up and started doing the Sudoku, that I realized, well, yes, actually, this could be interesting. No, I don't know what an optimal strategy would be. It is known, for those of you who know about computational complexity, if you take Sudoku and imagine it not on the 9 by 9 square, but on the n squared by n squared square divided up into n by n subsquares, it's NP hard. So that means there's unlikely to be a nice, efficient strategy for solving it. So that makes a good puzzle, right? When people tell me that a problem is NP hard, I don't just throw up my hands in horror and say, oh, we can't do it. I look and see, well, what can you do? If there are cases that you must know the answer to, then you just use brute force. But you might be able to solve some special cases more efficiently. So being NP hard is not the end of everything, but it does point to the fact that there won't be an efficient algorithm.
Thank you. Thanks for your patience.
My question was already asked, but I'm just going to say, if there is a good Sudoku problem in 3x3, we should call it a Sudocube.
Well, there are many variants of Sudoku, and some of them wrap around a cube. I don't know if there's any that... It would be a little bit difficult to actually print it in the daily paper and put the numbers in if it was a genuine three-dimensional problem. But there are some where you have, you know, a cube being unwrapped, so to speak, and you can trace the lines going this way and that way and want to get every number in. I think the Times has one of those, and I think they call it Tridoku or something like that. But yeah, good point.
Another question in from online. Oh, sorry.
It's okay, really we'll take the online one.
Yeah, that's great. Thank you. So the question is, can you explain a bit about how they came up with the number 17 for the minimum number of clues there?
Hard computation is the answer. You have to show that no arrangement of 16 numbers can possibly give you a genuine Sudoku. Many examples with 17 were already known. So the question was, can you do it with 16? And they just had to hack through the possibilities and show that it couldn't be done. It was a big computation. One here, another one over there.
Thank you. Could you please maybe talk a little bit about algorithms which are used to generate the Sudoku games as we see them in newspapers, for example?
I'm afraid I can't, but I do remember that in the very early days of Sudoku, some of them would appear in the paper saying, these have been produced by Japanese peasants working in something. I forget how they phrased it, but they tried to give you the impression that people had just sat down and created these puzzles. I don't believe that that's the way it's done now. But what you can do, you see, you can take a filled Sudoku and you can take entries out until, so if you have a computer program that solves it and tests whether there is a unique solution, once you take one too many entries out, there'll be more than one solution. So put the last entry back and you'll have a genuine Sudoku. So I think something like that is the basis of most of the algorithms they use, but I don't know for sure. I've never actually looked into that.
You really only just started talking about the 17 given situation. I'm aware of a gentleman by the name of Gerard Pinet and a team of people who've actually enumerated all the 17s and are now working on trying to enumerate all the 18s.
All right. They've got a long way to go to enumerate all the Sudoku puzzles, but that's a good start. Thank you for the information. I didn't know that.
So when you think about the Sudoku as having all the numbers in some way dispersed as much as possible, it's kind of like the opposite of a Rubik's Cube. So when I hear the number 17 over and over again, it reminds me of the number 20 with respect to Rubik's Cube. Could you think of a Rubik's Cube as being sort of a dual problem to Sudoku in some sense? Is there any mathematical thread there?
I don't know of any such thing. The point about the Rubik Cube is that essentially it's a group. And for groups, you pick your group theory book off the shelf. It tells you about generators and stuff like that. You're looking for a minimal generating set for that group. But Sudoku, symmetric Sudoku, I tried to convince you that it does have a beautiful mathematical structure. It's essentially a finite geometry, four-dimensional affine space. But ordinary Sudoku just simply does not have that kind of beautiful structure. So I don't see now any way that you could find a real duality between those problems. Now, someone will come along tomorrow and prove me wrong. Well, that's great if they do, but just I can't see how it could possibly work.
I'm familiar with the concept of naked pairs in Sudoku. How do they factor in with the idea that every Sudoku has a quote-unquote unique answer?
Well, if it doesn't have a unique answer, it's not a Sudoku. That's simply the definition. But I don't think there's an efficient algorithm for just looking at something that purports to be a Sudoku and deciding whether it is a Sudoku or not. And I suspect that, like that NP-hard result, that question in general is also NP-hard, which will suggest that there's no simple algorithm for doing it. The way to test whether something is really a Sudoku is to try and solve it. And if you get stuck, it's not a Sudoku. If you get to be able to make a choice, both of which complete, then it's not a Sudoku. But I don't know of any closer connection than that. And I suspect it's a hard problem.
One more question in from online here. It's kind of two questions in one, so in the interest of time, we'll just kind of take the second one. I think we found the mathematician in the online audience. Saying at Caltech, our first assignment was to design a mental network to solve Sudoku, and it found many global minima and solutions as well. How big can the landscape of solutions be for large numbers?
For large numbers? So, yeah, we've got the numbers for 9 by 9. For large numbers, well, the number of Latin squares is an upper bound. I would strongly suspect that there's a lower bound of the same form, n to the power constant n squared, where n is the size. But I don't know if anybody's proved that. It shouldn't be too hard to prove if you're a mathematician. Have a go. I think that sounds like a doable problem. And so that'll tell you the size of the landscape. It won't tell you the shape of the landscape, but it will at least know something about where you're looking.
We have time for one more in-person question, if there is one. All right. Then I'd like to thank Professor Cameron for joining us. Let's give him a big round of applause. Your presentation helps keep Richard's enthusiasm for mathematics alive for all of us here. Our students, faculty, and staff, and alumni and community members have all been made richer by the legacy and leadership of Louise and Richard Guy, that they've left to us, the Department of Mathematics and Statistics, the Faculty of Science, and the University of Calgary. It's through gifts like the Louise and Richard Guy Lecture Series and the Dr. Richard Guy Memorial Scholarship in Mathematics that the University of Calgary is able to offer opportunities to explore diverse perspectives and research, not only from our own brilliant academics, but also from those from around the globe. On a final note, we want to hear from you, so when you see our event survey in your inbox, please take a moment to fill it out and provide us with feedback. I'm going to interject one more thing. I have not recognized yet the numerous people who have done all the work in making this event actually happen. I'd like to acknowledge my colleagues, Marnie Ferrant, Melissa Rubleski, Melody Harris, Coral Burns, Renata Scheidler, and I hope I'm not missing anybody. If I am, I apologize. So maybe a big round of applause for all of those who helped make this event happen. Again, thank you for coming and enjoy the rest of your evening.